Six Sigma Measurement System Analysis. Now we're going to continue in the measure phase by discussing Measurement System Analysis, or MSA. This is one of the most important topics in the measure phase because Lean Six Sigma depends on data. But before we trust the data, we need to ask an important question. Can we trust the system that produced the data? Measurement System Analysis helps us answer that question. If our measurement system is unreliable, then every decision we make from that data becomes questionable. That includes root cause analysis, process capability, control charts, improvement validation, and customer acceptance decisions. What is MSA? Measurement System Analysis evaluates how much variation comes from the measurement process itself, rather than from the part or process being measured. In other words, when we see variation in the data, we need to know whether that variation is real process variation or whether it is being introduced by the measurement system. MSA answers a fundamental question. Can we trust the data we use to make decisions? If the answer is no, then all downstream analysis becomes unreliable. This is why MSA comes early in the measure phase. Before we use data to analyze the process, we need confidence that the data accurately represents what is happening. Why MSA is critical in manufacturing. Manufacturing decisions depend heavily on measurements. We use measurements to decide whether a part should be accepted or rejected. We use measurements to decide whether a process needs adjustment. We use measurements to interpret SPC signals. We use measurements to calculate CP and CPK. So, if the measurement system is poor, the consequences can be serious. Good parts may appear defective, which can lead to unnecessary scrap, rework, sorting, or customer delays. Bad parts may appear acceptable, which can lead to escapes, customer complaints, warranty issues, or assembly problems. Process variation may be distorted, which means we may not understand how the process is actually performing. And in the worst case, we end up reacting to measurement error rather than actual process behavior. That is a dangerous situation because it can cause teams to adjust stable processes, chase false signals, or miss real problems. What makes up a measurement system? When we hear the word measurement, many people immediately think of the gauge or instrument. But a measurement system is more than just the tool. MSA evaluates the entire measurement process. That includes the gauge or instrument, the operators, the measurement method, the fixturing and setup, and the environment. Environmental conditions can matter a lot. Temperature, lighting, vibration, humidity, cleanliness, and even noise can affect measurement results depending on the characteristic being measured. The operator also matters. If two operators measure the same part differently, then the system may not be reproducible. The method matters as well. If the work instruction is unclear, or if the measurement technique allows too much judgment, then the results may vary even when the part has not changed. The key point is this. MSA evaluates the combined effect of all these factors. We are not only asking, is the gauge calibrated? We are asking, can this entire measurement process produce reliable results in real use? Understanding variation sources. When we look at measured data, the total observed variation usually comes from two major sources. The first is actual part-to-part variation. This is the real difference between the items being measured. The second is measurement system variation. This is variation introduced by the gauge, operator, method, setup, or environment. MSA helps separate these two sources so real process behavior can be seen. That distinction matters because we do not want to confuse measurement noise with actual process variation. If measurement variation dominates, then true process changes can be hidden. SPC signals become unreliable. Capability results become misleading. And improvement decisions become risky. A simple way to think about it is this. If your measuring system is noisy, it becomes harder to hear what the process is actually telling you. Key elements of MSA. MSA evaluates several important characteristics of a measurement system. The first is accuracy, also called bias. Accuracy asks, does the measurement hit the true value? For example, if a part is known to be exactly 25.000 millimeters, does our measurement system read close to 25.000, or does it consistently read high or low? The next major concept is precision. Precision refers to how consistent the measurements are. Precision includes repeatability and reproducibility. Repeatability means the same operator measures the same part with the same gauge multiple times. If the results change significantly each time, repeatability is poor. Reproducibility means different operators measure the same parts. If each operator gets different results, reproducibility is poor. MSA also looks at stability. Stability asks whether the measurement system drifts over time. A system may work well today, but become unreliable later due to wear, calibration drift, environmental changes, or method changes. Finally, MSA looks at linearity. Linearity asks whether accuracy is consistent across the measurement range. A gauge may be accurate at one size, but less accurate at another. Together, these elements help us understand whether the measurement system is accurate, consistent, stable, and usable across the required range. Gauge R&R, the core MSA study. One of the most common MSA studies is gauge R&R. R&R stands for repeatability and reproducibility. Gauge R&R measures how much of the total observed variation is due to the gauge and how much is due to the operators. It compares measurement variation to total observed variation. The goal is to understand whether the measurement system is good enough to distinguish real differences between parts. There are common interpretation guidelines. If gauge R&R is less than 10%, the measurement system is generally considered acceptable. If it is between 10 and 30%, it may be conditionally acceptable depending on risk, application, customer requirements, and the importance of the characteristic. If it is greater than 30%, the measurement system is generally considered not acceptable. The key question is, can this system reliably separate good parts from bad parts? If the answer is no, then we should not rely on that data to make accept/reject decisions, process adjustments, or capability conclusions. MSA and Statistical Process Control, or SPC. MSA is also a prerequisite for effective statistical process control. Control charts assume that measurement variation is small compared to process variation. If the measurement system is poor, the control chart may show noise instead of meaningful signals. That can create several problems. False alarms may increase. The chart may appear to show special causes when the process itself has not actually changed. Real process shifts may be missed. If the measurement system is too noisy, a true process change may be hidden in the measurement variation. This leads to bad decisions. People may adjust the process unnecessarily, ignore real issues, or lose confidence in the control chart. A simple way to say this is, bad gauge, bad SPC, bad decisions. Before we use SPC to monitor a process, we need confidence that the measurement system is capable of detecting real process behavior. MSA and Process Capability, CP/CPK. MSA also matters before calculating process capability. CP and CPK assume that the measurement system is adequate. If the measurement system adds too much variation, the capability results become distorted. Excess measurement variation can artificially lower CP and CPK. It can make a capable process look incapable. It can also mask the true capability of the process. This is why MSA should come before capability analysis. If MSA fails, then CP and CPK results are not valid. In other words, if we cannot trust the measurements, we cannot trust the capability calculation. That is especially important when capability results are used for customer approval, production release, supplier qualification, or critical to quality characteristics. Capability example. Let's look at a simple example. Suppose we have a CTQ tolerance of plus or minus 0.010 millimeters. Now suppose the measurement variation is plus or minus 0.008 millimeters. That means the measurement system variation is almost as large as the tolerance window itself. Even if the actual process is stable and centered, the gauge cannot clearly distinguish between in-spec and out-of-spec parts. Some good parts may look bad. Some bad parts may look good. Capability results become misleading because the measurement system is consuming too much of the tolerance. This is not primarily a process problem. It is a measurement system problem. Before we blame the process, adjust the machine, or launch a major improvement project, we need to fix or improve the measurement system. DMAIC alignment. Let's connect MSA back to DMAIC. In the define phase, we identify the CTQs. These are the customer-critical characteristics that need to be measured and controlled. In the measure phase, we perform MSA and validate the measurement system. That validation gives us confidence that the data we collect is reliable. In the analyze phase, We use that data to identify root causes. If the measurement system is valid, our analysis is much more trustworthy. In the improve phase, we use reliable measurement to confirm whether the process actually improved. In the control phase, we use reliable data for SPC monitoring, control plans, and ongoing process management. The message is simple. No validated measurement system means no valid improvement. MSA protects the integrity of the project. It makes sure that the data we use to make decisions reflects the process and not the noise of the measurement method. To summarize, measurement system analysis helps us determine whether we can trust our data. It evaluates variation from the measurement process, including the gauge, operators, method, setup, and environment. It helps separate true process variation from measurement system variation. It supports reliable SPC, valid CP, and CPK calculations and better decision-making throughout DMAIC. As green belts, we do not need to become metrology experts, but we do need to understand one critical idea. Before we analyze the process, we must validate the measurement system.